Thanks for joining us today. I'm Shaun Hopper,
I'm Chandan.
and we're production engineers at Meta. Today we're going to talk about how we sort of evolved the AI research infrastructure by moving to Kubernetes. First, to start it off, we're on this team called Cloud Foundation. So you might think of Meta as this company that has its own private infrastructure. They do everything like custom for their workloads and things like that. They manage their own data centers. That's all true, but that's not what we do. So we're on the team that builds sort of all the frameworks and tries to establish best practices for doing things when you have to use the public cloud. So that looks like sort of coming up with ways to run machines, providing base images, how to run Terraform, how to do things in a compliant way, like sort of pretty much everything but running the application and infrastructure ourselves in the cloud, with the one exception being these massive scale like HPC clusters. So in those cases, we do actually run those environments, but in the day-to-day, we're just building the tools so that when other teams at the company need to use the public cloud because they can't use the on-prem infrastructure, they come to us. We wanted to focus on three major sort of tenets that we were trying to either preserve or learn from as we did this migration, and they fall into these three buckets. So we either wanted to at least preserve the research experience or make it better. We had to come up with new ways to manage hosts, and we had to ensure that in the new environment we properly had data access controls in place. Obviously nothing could go backwards, right? That's how these things align. In order to even talk about how we could move the research environments from one type of infrastructure to on top of Kubernetes, I first want to just kind of go over what the Slurm experience looks like for a researcher. We typically think of, well, first of all, Slurm is like a resource management / scheduling sort of orchestration system that researchers typically use because it has pretty deep ties in academia. So to researchers, Slurm is like the interface to doing research. And we like to think of it like this. So there's three sort of pieces of the Slurm deployment. There's the login environment where you basically get an SSH session, you log in, this is where your home directory is, where you prepare your experiments. You basically kick off your research jobs from this environment. And then you talk to the Slurm control plane, which is in green. It's a few various components, but the main one to think about is Slurm CTLD. Slurm CTLD is what you'll talk to actually schedule your workload. So you're in the login environment, you say, I want, I don't know, 100 GPUs and this much RAM or whatever. You talk to Slurm CTLD. You might talk to Slurm REST, which is just an HTTP interface in front of Slurm CTLD. But ultimately, you talk to the control plane. It stores it in a database. And if the resources are available, it will look at the Slurm D down in yellow worker nodes and appropriately provision you the resources you need, and then start your job. So we'll use the term Slurm D and worker sort of interchangeably. You might even call it compute node. So yeah. With the Slurm piece out of the way, I kind of want to go into what the infrastructure of the hosts looked like before we moved to Kubernetes. So we pretty much have split the deployment on top of either CPU nodes or GPU nodes. And we run this thing that we call meta instance, which is, it's sort of just like a base, either CentOS or Ubuntu distribution, which we can then bake our platform binaries into. So you can imagine it as pretty much an image you pull off the shelf for doing pretty much whatever you want, and we bake in all the quality of life daemons in that sort of yellow containerized meta instance layer. And This layer doesn't change pretty much no matter what you're doing on top. So we have like all the way up to the yellow is this just base layer that will do anything in the cloud with. But then on top of that, we have the Slurm components that sort of turn the meta instance into like suddenly an HPC cluster, right? So on the right side, the CPU nodes will do things like run that control plane. We'll have the login sessions and things like that. And then on the left-hand side, the GPU nodes, we're not going to like waste running control plane components. That's where we run Slurmd. And on both of them, we're managing things with Chef. And Chef, for us in this case, was kind of like the sore thumb that stuck out. Everything here is running in a container, except for Slurmd, and we'll get to that in a second. But Chef, I mean, if you know, sort of has this, it's based on this model of like promise theory, right? Where you say like, I have this machine now, and I want it to be this machine later, and on some interval, it's gonna run, and it's gonna try to converge that machine to that state. That totally works fine, but we found that over time, depending, like, since the rest of the machine is mostly immutable, we ran into all kinds of weird issues where, like, if you built the machine image 6 months ago, and then you booted it 6 months later, it's actually like not the same thing as if you booted it 6 months ago and ran Chef every 15 minutes, and you inspected a machine that did that today versus one that started back then. And it was just becoming sort of this like untenable thing for us as we were like so invested in containerizing everything on the machine, but still like controlling a few systemd units here and there with Chef, and trying to like patch things at runtime. So like a big motivating thing for us was to get rid of the Chef piece and try to use Kubernetes to do all of the orchestration. The last piece that was not containerized is the Slurmd piece. And for us, it was easy to containerize everything else. Slurmd, if you think about what it's doing at its core, is actually doing the same thing that starting a container does on Linux. So Linux gives you a few knobs to isolate resources, right? You get C groups, you get namespaces. When you ask Slurm to make you a job, it's going to use the same things. So we were a bit hesitant to just go straight for the kill, to sort of run Slurmd inside of a container, which is going to be, you know, C grouped and namespaced off, and then you kind of have this like Russian doll problem that we didn't want to go straight for. So this is kind of how things ran, and then we knew we wanted to do something else. So we wanted to rip out the base layer and sort of think less about that whole meta instance concept mentioned before, where we have some like CentOS or Ubuntu, we layer the daemons on, we bake it into an immutable image. We wanted to like not think about the image at all and just have Kubernetes, and then as images come and go, whoever the provider, like whatever the image, we just think of it like one layer higher. As long as the kubelet's running, like it's good enough for us. So we thought we'd do something like this. We still have the control plane components running on the CPU nodes on the right-hand side, and we still didn't want to tackle the Slurmd problem of sort of running a container in a container. So we started working towards this, but we actually ended up with this. So it's pretty much exactly what we thought we were going to do, but we ended up putting the Slurmd in a container anyways. We have this little red piece in the middle, which is just layer 3 connectivity, and then we control all the network sort of ingress and egress on the right-hand side. And the reason this is super valuable for us is because we can keep the right-hand side completely constant in any cloud provider we want, while on the left side, as long as the cloud provider provides us Kubernetes, we can pretty much take the whole stack and run an HPC cluster wherever we want, which I mean, to us is immensely valuable. I'm not sure how you and your companies are finding GPUs at the moment, but to us, it's super valuable. So with that out of the way, that's sort of like the background. That's how the infra worked. We'll go straight into the first thing we focused on, which was preserving the research experience. And for us, one of the major components there was that the experience for them needed to be consistent, but if we could make it better, then it's better for everyone. We didn't want it to be such that like our choice to use Kubernetes had some impact on the researchers. So like from day one, we decided like the researchers will never even know that their Slurm cluster is running in Kubernetes. In practice, like we all talk to each other, so like eventually, like yes, it's understood by them that it's running in Kubernetes, but they're not actually Kubernetes users. They don't have kubectl installed on their laptops. They don't have Helm installed. Everything is containerized and abstracted away for them. And it's still split up into those three sort of subcomponents for Slurm, with the login environment, the control plane, and the worker node / slurmd. And those are all just controlled via a Helm chart. And that Helm chart is called the Slurm chart, and it's just deployed in different ways depending on what we need it to do. So on the next slide, I'll kind of get into that. But the green control plane and the worker nodes are deployed just as normal Slurm Helm chart, and we just sort of disable the pieces we don't need so that we can update them independently and things like that. The one exception to that is the login pods themselves. So in the previous architecture, we would have a fixed number of machines that researchers could log into and sort of prepare their jobs, kick off experiments and things like that. In the new architecture, like we're on Kubernetes now, so we could give every researcher their own pod, which comes with everything that's nice about giving a researcher access to Kubernetes without them realizing it, right? So things like noisy neighbor issues where 3 to 5 researchers are SSH'd in the same machine and they're causing the killer to kill each other's stuff and things like that, those things go away because it's just Kubernetes. So the login pod itself has resources and limits applied to it. And the Kubernetes scheduler can see like, oh, there's already 6 login pods on this node, but this CPU node has none. Like, I'm going to put the next one over here. So we got access to all of the like nice things that Kubernetes provides, but we had to solve this problem of like, how do we let a researcher provision? Basically, how do we let a researcher run Helm without them realizing it? And to do that, we had to create our own CLI. So if you know, Kubernetes presents its entire interface as an HTTP like REST API. So what we did is we just really wrote a small piece of Rust code to do a post request of this thing in the green down here. So in the green, we have the Helm release CRD for the Flux controller. And if you don't know what a CRD is in Kubernetes, you can just think of it as a custom type. This type, in particular, is about deploying Helm. So we literally just let them say, hey, I'm researcher X, I'm deploying the Slurm chart, and here's all the configuration I need. And we lock it down so that they actually can't change anything about that request other than their name. So they just submit this to the Kubernetes control plane. It goes up one layer into the admission controller, which sort of, if you don't know what an admission controller in Kubernetes is, you can think of it as something that's running at runtime, intercepting the requests, and doing like extra sort of auth-z related evaluation. In that layer, we just say, hey, is the researcher doing anything other than exactly what we expect? If they are, it's rejected. If they aren't, it goes through. So most of the time it goes through because the researchers don't really know they're using Kubernetes anyway, so they wouldn't forge a request. They submit their Helm release, and then the Flux controller is watching for the Helm release type, and it will just deploy the login pod for them. After the login pod is ready, this all happens in a few seconds, it just drops them into an SSH session directly into the login pod, and now they're running Slurm commands inside of Kubernetes without realizing it. Yeah, okay. With that, that was sort of like the preserving the research experience part, but there were the other pieces around host management and data access control that Chandan's going to cover.
Okay. So, as Shaun covered, as we moved from the running host and chef on the host and managing a lot of things using config management to Kubernetes, we did not want to do much at the host level. So we wanted to use Kubernetes run pods. It's much easier for us to manage across various cloud providers, but we couldn't totally avoid doing host management. So we still had to do few things at the host. So next few slides we'll cover how our host management changed. Uh, so yeah, so we pretty much use OS images provided by cloud providers, which comes with uh, containerd, kubelet, whatever essential things that are required for the host to be used as a Kubernetes node. And pretty much we treat that as a immutable host at that point. And because like it becomes hard to manage across various cloud providers, like various OS distros and things like that. So we don't want to like deal with those problems by because like we learned a lot of lessons earlier with the existing infrastructure that we had that we have been using. Uh, so across the cloud provider, like we know, like okay, Kubernetes is going to be our interface, so we can utilize that to do the host management. In some cases, we don't even have the SSH access to the host, so and then we did not also wanted to bother like configuring another interface and maintaining that because like we have Kubernetes and we know we could make utilize that to do whatever the admin access requirements that we have to satisfy. Uh, so to do the host management, basically we use Kubernetes daemon set. So Kubernetes daemon set is a deployment type in Kubernetes that you can use to uh, run one replica of the pod across all the nodes. And we run it in the privilege mode, so pretty much you can control the access of what kind of privilege that particular node pod needs according to the need, according to the what that pod is supposed to do. So on the screen here, you see an example of admin pod. So this is essentially a landing zone for us. So whenever we have to do any kind of like troubleshooting or profiling on the host, we use this login pod as a landing zone. The host root is mounted, bar mounted inside the admin pod, and then pretty much any troubleshooting, any profiling we have to do, we just utilize the login pod. So this kind of also gives additional benefit. If somebody installs something on the host, it doesn't go directly on the host, it stays inside the admin pod, and we can just recycle this admin pod, and that thing goes away. So it kind of like avoids making host dirty by doing certain things when you're troubleshooting. Um, like I mentioned earlier, like in terms of host management, we do few things at the host, such as like configuring kernel parameters across the fleet and in a consistent way that is required for us to run our workloads. So for that, we run a host CFG daemon set that just runs the sysctl and configures the kernel parameters for us. One more example of that. One more example of host level uh, daemon set is auto mount that continuously mounts the NFS file systems on the host across the fleet. We'll see more on that. That is actually our next challenge. So in the AI cluster, typically, at least for us, uh, provisioning a new file system or introducing a new data sets or introducing a new volume is a routine task. And as you can imagine, AI workflows are long-running batch process jobs. They don't like to be disturbed. So even though like we have to uh, constantly provision like new file systems and volumes, we cannot just uh, take a downtime to introduce those things. And Kubernetes way of doing things like introducing new volume or file system is using like volume mounts on the pods provided by CSI drivers and persistent volume claims, but that needs an pod restart whenever you want to introduce a new volume. So that isn't going to, like that did not work, that just doesn't fit the requirement here. So we had to kind of like look at the alternatives. So we come up with this auto mount daemon set and a provisioning mechanism for the NFS file systems, and then pretty much we end up using NFS for all our storage needs for our AI cluster. So on the left-hand side, you see an NFS provisioner, and then it mounts a config map that has list of file systems that need to be provisioned and in a certain way. So that is managed through a code repository. Whenever a new file system is needed to be provisioned, we just make a code change, and then NFS provisioner takes care of provisioning it. It also triggers another change on the in the automount daemon set. There is a fs tab config map that has list of things it needs to mount whenever it continuously like make sure it is mounted on the host. So whenever new file system is provisioned, that config map gets updated by our automation, and the file system gets mounted on the GPU. One more thing that we had to do to make this work is categorize these file systems into various categories. So as you can see on the screen, there is a checkpoint, datasets, and infra. So those are like parent directories that are created on the host, and then those parent directories are mounted inside the pod. So for the SumD and login pod, basically nothing changes. The new datasets just appear and disappear down the line in those parent directories, and then we don't have to like do any restarts on the slumd or login part. So this provides a seamless way of introducing new datasets or provisioning ones which are not needed, or deprovisioning ones which are not needed anymore. With that, we moved to our next challenge, which was around doing a proper data access control. And since we are now pretty much like wanted to do in everything through Kubernetes, we had to find certain new ways of like doing things in this area. So at Meta, our internal and external access systems use X509 based certificates. And as you can imagine, if you want to do any kind of like access control and have ability to like audit stuff, like who is doing what in the cluster, you need some kind of a way to give those entities identity in the cluster. So for us, primarily it was users who are logging into the cluster and running the job, and also services that we run inside the cluster that might be also talking to various other services within the cluster. So we needed a mechanism to make sure we have ability to generate the certs using our own private CA, and to be able to make it available inside the environment so that in the Kubernetes pods that can be utilized. So as a solution, we use Cert Manager. Cert Manager is a open source, very popular tool that is used on popular tool in the Kubernetes community that handles cert management. It also provides a way for you to like extend it and integrate with your own private CA. So to make this work, we implemented our own custom controllers. So here you can see like there are two custom controllers. Green flow covers the user certs flow, and the blue covers the service cert flow. Pretty much they work the same, but we decided to implement like two different controllers because they do two different they work a little bit differently, as the validation parts are vastly different between what we do on the user identities versus service identities. They can be also independently used in various other environments as well. So we just kept them separate. So the way it works is Cert Manager provides a custom resource definition that we can use. So that gives us the ability to create a custom resource within Kubernetes. And that resource is just definition of what certificate we need. So we provision, we create those objects, and then Cert Manager is continuously observing those objects. And whenever it sees a new object or it sees an existing cert is expiring, it generates the certificate request and then sends that to appropriate controller. And then our user and service identity controllers talk to our private CVA and generate X59 cert, and once that cert is received, it can be mounted. It can be. It is stored as a Kubernetes secret, and then pretty much those secrets are mounted inside the pod. You can also use a CSI driver as well with cert manager, and that will make the cert available directly inside the pod. Um, so this gives us ability to uh, generate the certs inside the Kubernetes and mount inside the workload. And then pretty much we use that certificate to, for example, talking to object store internally, and also whenever anything needs to go and talk outside of the cluster, like access any internet endpoint, that request needs to go through our egress gateway, and that egress gateway also has a mutual TLS authentication that also needs a cert. So that is covered a little bit in more depth in our in the next slide. So here in the red box, you can see there is the egress gateway, which is essentially a forward proxy that sits in front of the cluster, and anything going outside the cluster goes through that egress gateway. And to be able to like talk to the egress gateway, you need a certificate that we saw earlier. So now we have a certificate, and we have egress gateway that provides you ability to like talk to anything, any allowed domain outside of the cluster. But that was not enough uh, because like typical research workflows involve doing things like git clone, pip install, rsync, copying like data sets from various places, configuring Conda environments. Some of these things don't really support utilizing the client cert. And so we needed to find some way we can give researcher ability to utilize client cert. One more important aspect was researchers could use different clusters within Meta, and we did not want them to, we wanted like researchers having to change their workflows to kind of like configure the proxy, configure the auth, and like instead like we wanted to see if we can provide a seamless way for them to utilize the cluster without having to worry about cluster specific configuration details. So to solve this problem, we run a, a sidecar, which is shown in yellow here. We call it like transparent TLS proxy container. Uh, it runs an eBPF program that intercepts any outgoing TCP packets, connections, and it checks if it is destined to go outside and talk to the, like it is, if it is internet traffic, uh, it, it, it encapsulates that inside the HTTP connect connection, and it also utilizing the UID of the TCP connection. It loads the user cert, and it forwards that request to our egress gateway. On the way back, there is another eBPF program that runs and writes back the packets to the client. So in this way, client is not even aware like something is happening, or they have to like utilize this, they have to do a mutual TLS authentication or talk to the forward proxy. So automatically, whenever somebody is talking, like accessing the internet, the request goes to the forward proxy, and everything is kind of like audited. So those are some of the useful challenges that we thought like are valuable to share here, and useful for you. But we have been running this cluster for a while now, and it showed like a lot of improvements, but we are not done here. As you can imagine, we are poised with some new challenges, and we also wanted to share that here so that just don't want to like have a like paint a pretty picture. Uh, so as we run login nodes as a pod now, any new feature rollout needs a login pod restart. Any node maintenance needs a login pod restart, and that kind of like causes a lot of disruption to the researchers, because they continuously, their term sessions get killed. They have to like restart whatever the work they left they were doing. So initially during the when we launched this cluster, we had some friction, so we had to come up with some solutions to make it workable. So right now what we do is we use TTLS, that is that like time to leave kind of a mechanism. So as Shaun mentioned earlier, we run a Kyverno policy engine. Using that, what we do is we run login pods for 7 days, and after 7 days, those login pods are automatically garbage collected. So during those 7 days, we don't roll out any new features so that like uh, they don't, like the researchers, they don't get disturbed during these 7 days. So whenever you log in for the first time, your pod gets created. Then after that, this stays there for 7 days without any disruption. And whenever, after 7 days, that login pod gets garbage collected, and um, then whenever you log in next time, your login pod comes up with a new image, new Helm chart, new features. Uh, there was also we also, because this was still a new cluster, we were introducing a lot of new features. We also had to frequently schedule node maintenance. So that also required a lot of restarts. So for now, we kind of came up with a mechanism where we maintain two different types of pools of nodes. Something like green-blue deployment, where we only do node maintenance when the pods are completely drained after they expire in 7 days, and then we can do maintenance on those nodes, or work with the cloud provider in some cases to do the maintenance. One more challenge that we have is size of the images, because everything kind of deployed as a inside the image, and as you can imagine, for AI workflows, sometimes they need various versions of CUDA, they need various versions of Conda and stuff like that. So things can grow pretty fast, and you can easily have 10 GB image that you need to deploy. And as the nature of this environment, because we are spinning things dynamically, we don't want people to wait even few seconds when they log in and their login pod is still downloading the image, and constantly they have to wait. So as a short-term solution, what we have been doing is we have been using NFS share to kind of maintain a lot of large packages such as CUDA, which take a lot of space, and we also have to maintain a lot of versions of it. So we use NFS share. So that kind of solves the problem, but makes it a little bit harder to automate things and implement continuous integration, continuous deployment. So we are looking into, I think soon we'll move to utilizing a new feature in Kubernetes 1.31, that you can now use external, a container image as a volume, so you can have different images for different things, and you can mount those as a volume. So that might be probably a solution that we might try um, and see how it works. One more thing that we have been having challenges is canary deployments. As we went over a little bit earlier, we run many things as a Kubernetes daemon sets, and so everything gets deployed across the fleet. And in Meta, we depend on canary deployments a lot, because of we deal with a lot of scale as well as a lot of complexity. So every single thing we cannot test before the hand, even though there is a staging and there is a continuous integration mechanisms to do it, but not always possible to do it, because, for example, something only fails when you have NFS volume with billions of small files, versus when you run in the pre-staging or test environment, that scale isn't there, and then things just work, but you only see problem when you deploy to the production environment. So typically, we do canary deployments where we shard the deployments in various percentages. So in Kubernetes right now, what we are doing is we are just splitting the daemon set into multiple Helm releases, and then we are sharding nodes using the node labels. So in that way, we still have to manage multiple Helm releases, but it is somewhat workable, but not ideal. So in the near future, we'll be looking into implementing a custom canary deployment controller, which can provide a better way to do the canary deployment, and that suits our need, basically. One more challenge that we continuously face is We saw TTLS proxy earlier. It kind of like works in magical way behind the scene. And also we run things like Kyverno that just makes our life easier as well because it does a lot of things in the background. But things like that are good until they work. But as soon as you start having issues, it is extremely difficult to troubleshoot and find out like what's going on. So we definitely want to work on improving our troubleshooting and uh, debugging story there. So that brings us to end of this presentation. We also want to thank a lot of open source project that has been very helpful for us uh, to build this cluster and make it usable. So big thanks to open source community. With that, we will take the questions, and we'll also be available later on in the hallway if anybody want to chat.
If people have questions, I'll run the mic.
So it's interesting to see your use of NFS. So are the systems acting as the NFS server, are those in Kubernetes as well?
In some cases, yes. In some cases, no.
And through the, I forgot the name of the project, but there's a protocol to handle to facilitate the storage, I mean, is it mounting any storage directly, or it's all the file systems mounted via NFS?
Yeah, so in this case, at least the example that we shared is just NFS, like plain NFS mounts. And the actual server side can be different based on the cloud provider. But that kind of like doesn't really matter. On the like cluster, we mount it as a NFS. That's it.
Cool.
How does this effort relate to the sunk effort being done by SkedgeMD, their Slurm under Kubernetes effort that they have in-house? Is this something that you'll have done in parallel with them and are aware of how they're doing that, or is it, I guess I'm just asking because I see y'all talked to the Slurm team and they have their public Kubernetes effort.
Yeah, like, is this working? Like, we don't work with Slurm. Yeah, that's pretty much as far as it goes. Like, it's a big company. There are other people that do, but as far as like what we're talking about here, like, we don't work with Slurm.
Thank you first for this nice presentation, both of you. I know this is not the main point, but like the data is so important in these AI workflows. I would like to ask again about the NFS. Like, first of all, it's very interesting that you're using it, and also the idea with the container images is it seems also quite useful. Are you so? As I understand, you're serving some of the software through it because like it just makes it easy to distribute everywhere. But are you serving also all the data through NFS and not using object storage, let's say, in the cloud providers?
We use object stores and NFS to both store or serve. Like, it's all used. Yeah, I'm not exactly sure what the question is. Yeah, all of the training data and checkpoints and things like that are just NFS mounted on the host and then bind mounted into the container. So that allows us to keep like a high level bind mount, and then as the new data comes and goes, it's just a subdirectory on what is already bind mounted into the container, meaning that the container lifecycle is unaffected and the data can come and go. It's really just a bash for loop running in a daemon set that's running the mount over and over and reading config map for updates.
Yeah, so there are other data sources as object store as well, but like we don't need to do anything, like we don't need to do any mounting on the, that's why it's not covered here. So it's mostly like, okay, if you need a specialized client, that client gets installed inside the pod, and then pretty much you can access whatever storage you want to access. But in some cases, you have to mount the storage on the host or pod. So that's where like challenge comes in when you run things in Kubernetes, because without restart, you cannot really mount it. So.
Given the nature of this program, is there any plan from Meta to contribute back to the Kubernetes community?
I think like not on the Kubernetes, because Kubernetes is very small footprint as compared to like rest of the Meta. Yeah, but we do contribute in other like open source like projects as well, but not specifically for Kubernetes yet.
Like just to set the scale of things here, like our team is very small. When I say like we're doing Kubernetes, it's really like 3 people that really know what it is. We have to make this happen. It's not like the whole entirety of the company is using Kubernetes and has the ability to like get invested and write PRs directly to Kubernetes and things like that. But I think as a company, we've definitely contribute to open source and things like that.
So you mentioned that you're supporting researchers that are using public cloud infrastructure. Is that correct? Okay. Like why do they do that? Like why not use like the internal infrastructure?
Yeah, so capacity basically, right?
Okay.
Wherever you find the capacity.
Okay,
is
so
there,
it's
like,
not
the-
enough to service all of them internally.
And I think it's not as much that the researchers are using the public cloud as much as they need access to Slurm, and we're going to stand it up wherever we can for them.
Okay, I see. Thank you.
Any other questions? All right. Thank you guys very much.
Thank you.